the general theory of relativity. So in 1915, Albert Einstein writes this paper, and interestingly enough, he had started to think about it. Well, after special relativity itself, he started to think about, well, what if we start changing these frames to non-inertial frames? But in 1907 was the first, I believe, the first instance of him actually thinking about the relationship between acceleration and gravity, and thinking about, well, is gravity, what we see on Earth, the same thing as accelerating in a spaceship? And this is the very famous this is one of Einstein's postulates, where you flying in a spaceship is the same as you on Earth. And you're like, well, how is that possible? And that is basically, a consequence of what he proves here. So the general theory of relativity is basically a way to say, screw you to Newton, and say that, well, gravity isn't anything. It's not really a force or anything. It is simply a consequence of what we call the space-time manifold. What we call space-time, or space, well, what we call space, when our Earth is sitting on some block of space, gravity is simply the consequence of that block having mass. Anything with some amount of mass will depress the space-time the space-time curvature, like it's called. And he came up with this idea that, well, gravity isn't really an attractive anything. It's not a force whatsoever, but it's simply because, well, space is curved. So everywhere you're going, the reason you look like you're moving in an orbit is not because you're actually moving in an orbit. You're just going straight. But it's space that is actually curved around the body to make it look like a circle. But what you're actually doing is simply going straight, but it's space that's curved. So he explained what we see in reality, in nature, in a radically different way, using the general theory of relativity. And I believe he published it actually in 1916, and then in 1919, a bunch of astronomers, as you were mentioning before in the podcast, they were witnessing an eclipse where they saw the first proof of gravitational lensing, i.e., gravity bending light. Again, if Newton was right and gravity is a force, gravity should not affect light, right? Because light is massless. However, Einstein proved that, again, gravity has nothing to do with mass, or at least not the mass of the object. It's simply with the curvature of space-time. So because space-time is curved around the sun, we can see objects that we generally would never be able to see because of the fact that the light is curving. And again, this was simply a consequence of his general theory. And that's Einstein for you, revolutionized science in 20 years. Less.
A
Crazy.
Great way to think about this, which is, it always blows people's minds when they think about this. But imagine this, okay? Imagine you have a rock and you're in the middle of deep space. There's no gravitational field anywhere around. And let's pretend like you're a ghost, you don't have a mass. Okay. So you're sitting in the middle of nowhere and you throw the rock. And the rock draws a path behind it, right? You're just going to see a straight path. It's going to float in a single direction at a constant speed. That's all you get, okay? Now, let's come back to Earth. You have that same rock, and you throw that rock in the same direction. What happens to that path? That path gets curved down towards the Earth. But that's not that has nothing to do with the rock. It has to do with where the rock is in space. It just so happens that the space is curving its path. And the thing about space-time and why it's so hard to think about curved space-time is because you need to consider the time dimension as well. And that's why I say imagine the path being drawn out. So in deep space, there's no curvature happening, right? You just throw the rock, and throughout space-time, all four dimensions, the path is completely straight, and it will continue to be straight. But on Earth, or let's say you're in Earth's orbit, and you throw a rock in front of you, that path, depending on the velocity of the rock, of course, but let's pretend it's going at
No,
the
well,
perfect
if you're in
velocity where
orbit,
it
if
can-
you're in orbit, it will remain in orbit, right? Because it's already traveling at like
Yeah.
7,000 plus kilometers a second.
Yeah, but let's say for example, you throw it like behind you and then it slows. But the point
Okay,
is,
well,
right,
I understand.
the point is that if you throw that rock is not just going to go in one direction and just keep going, because the space time that it's in is literally curved. And so that's going to, as time plays out, the path of that rock will be curved and you can literally see it with your own eyes. So,
And a very
I guess,
famous thought about bent space is, you know, like putting a ball on a carpet. But that's a terrible way to think about it, because what you think about is that the ball, that anything you throw outside will eventually come in. But that's just not how space works, right? That's just not how it works. There is a certain level after which you cross, you will go in, right? That is simply a fact with anything. If you're really close to the planet and your orbit, you know, has some certain properties of hitting the planet on your next cycle, well, you will hit the planet, you know. But if your orbit is large enough, again, that carpet definition doesn't make you understand it, because then again, it all eventually comes to the center. But that's not actually what space is. It's more like just a little blip, and then okay. I guess I can't really. I just thought about it. I can't really explain it too well.
Let's just,
especially
let's
to the
just
audio
cut this
listeners, this might be
explanation
terrible.
here.
There's not really a way to do it. But anyways, there are like, you know, visuals of how to think about curved space-time. So like you might want to search up. And again, this is all a consequence of the general theory of relativity.